Greetings everyone. Today, we're embarking on a journey into the intriguing realm of non-parametric tests. These tests, a crucial tool in the world of statistical analysis, are often employed when data doesn't fit the mold of a typical Gaussian distribution. Now you might be thinking, what's the big deal with these non-parametric tests? Well, they are a part of a larger family of statistical tests, which also includes their counterparts, parametric tests. While parametric tests assume underlying statistical distributions, non-parametric tests make no such assumptions, making them perfect for analyzing data that's a bit out of the ordinary. So, in essence, non-parametric tests are like the rebels of the statistical world, playing by their own rules yet yielding valuable insights. Intrigued? You should be. So, ready to delve into the world of non-parametric tests? Let's get started. Now the question arises, when should we use non-parametric tests? Well, non-parametric tests, also known as distribution-free tests, can be the perfect go-to when dealing with certain types of data. These tests are often preferred when the data does not meet the assumptions required for parametric tests. In other words, if your data isn't normally distributed, non-parametric tests can be a lifesaver. Parametric tests have several assumptions. For instance, they require your data to be interval or ratio level, and they also assume that your data is normally distributed. Furthermore, they assume homogeneity of variances, which means that the variances in the groups you are comparing should be roughly equal. But what if these assumptions are not met? What if the data is skewed or if the sample size is too small? This is where non-parametric tests come in handy. They are less stringent about the data they can analyze. They can be applied to nominal data, which is simply data that can be put into categories, and ordinal data, which is data that can be put into categories with a specific order. Moreover, non-parametric tests are robust against outliers. Outliers can often skew your data and give you incorrect results if you were to use a parametric test. But non-parametric tests are not as affected by these outliers, making them a reliable option in such cases. Additionally, non-parametric tests are excellent when dealing with ranks or scores, rather than actual raw data. For instance, if you were to rank a group of drugs based on their effectiveness, a non-parametric test would be the appropriate choice. So while parametric tests are powerful and useful, they are not always the best fit. Non-parametric tests offer a fantastic alternative for analyzing data that does not meet the assumptions required for parametric tests. Hence, understanding the nature of your data and the assumptions it meets is crucial in choosing the right kind of test. It's all about picking the right tool for the job. Scene script. Let's now take a look at some of the common types of non-parametric tests. First up, we have the Mann-Whitney U-test. This test is a favorite when we want to compare two independent groups. It's a bit like the student's t-test, but with a twist. Instead of making assumptions about the normal distribution of data, it ranks the data from both groups together and assesses whether one group tends to have higher or lower values than the other. In a nutshell, the Mann-Whitney U-test checks if the distributions of two independent samples are equal or not. Now let's move on to the Wilcoxon signed rank test. This test is employed when we are dealing with paired samples. Think of it as the non-parametric equivalent of the paired t-test. This test ranks the absolute values of the differences between paired observations. It then uses the signs of the differences to calculate a test statistic. For instance, if we are measuring the effect of a new drug on blood pressure, we might take readings before and after administering the drug, and then apply the Wilcoxon signed rank test to determine if there's a significant change. Last but not least, we have the Kruskal-Wallis test. This test is a non-parametric alternative to the one-way ANOVA, and is used when we need to compare more than two independent groups. Like the previous two tests, it also ranks the data, but does so across all groups. The test then checks if the average rank differs significantly between groups. For example, if we have 3 different types of painkillers, and we want to see if one is more effective than the others, the Kruskal-Wallis test could be our go-to. Remember, while these tests don't require the assumption of normal distribution, they do have their assumptions. For instance, the Mann-Whitney U-test and Kruskal-Wallis test assume that the distributions of the groups are the same shape, while the Wilcoxon signed rank test assumes that the differences between pairs of observations are symmetrically distributed. In the realm of pharmaceutical research, these tests are invaluable. They allow us to make robust statistical inferences when the data doesn't meet the stringent requirements of parametric tests. Whether we're comparing the effects of different drugs, assessing the impact of a new treatment, or analyzing patient responses, non-parametric tests can provide the statistical rigor we need. These tests, among others, form the backbone of non-parametric statistics in pharmaceutical research. Every statistical test comes with its own set of advantages and limitations. Diving right in, let's talk about the advantages of non-parametric tests. For starters, these tests are less sensitive to outliers, which can often skew results in parametric tests. This characteristic makes non-parametric tests more robust and reliable. Secondly, non-parametric tests don't require your data to follow a specific distribution, such as the normal distribution. This means that even if your data is skewed, you can still use non-parametric tests effectively. Additionally, non-parametric tests can handle ordinal data and nominal data, which are types of categorical data. This is a significant advantage, as a lot of real-world data falls into these categories. Now, onto the limitations. One of the main drawbacks of non-parametric tests is that they are less powerful than parametric tests when the assumptions of the latter are met. In simpler terms, if your data does meet the criteria for a parametric test, you're likely to get more accurate results with parametric tests. Another limitation is that non-parametric tests can't provide as much information as parametric tests. For instance, they don't provide estimates of population parameters, such as the mean or standard deviation. Also, the interpretation of non-parametric tests can be a bit challenging. While they can tell you whether there's a difference or association, they can't tell you the size of the effect, which is often a crucial piece of information. Lastly, while non-parametric tests can handle ordinal and nominal data, they can't deal with continuous data as effectively as parametric tests. Thus, while non-parametric tests offer certain advantages, they also come with their own set of limitations. In the end, the choice between parametric and non-parametric tests comes down to understanding your data and your research question. Remember, the best statistical test is the one that best fits your data and your research objectives. Non-parametric tests are not just theoretical concepts, they have practical applications too. Let's dive into a real-life example. Imagine a pharmaceutical company developing a new drug. To compare the effectiveness of this new drug against a standard treatment, they conducted a clinical trial. However, the data collected didn't follow a normal distribution due to various factors such as age, genetic makeup, and lifestyle of the participants. This is where non-parametric tests came into play. The company used the Mann-Whitney U test to compare the two independent groups, those who received the new drug and those who received the standard treatment. The test helped them determine whether there was a significant difference in the recovery rates between these groups. Now, let's add a twist. The company decided to conduct a follow-up trial where the same participants were given both treatments at different times. This time, the Wilcoxon signed rank test was used, suitable for paired samples. The test helped analyze the differences in recovery rates from the same group of participants. Lastly, the company wanted to compare more than two treatments. They used the Kruskal-Wallis test to compare the effectiveness of the new drug, the standard treatment, and a placebo. This real-world example demonstrates the practical application and significance of non-parametric tests in pharmaceutical research. So, to wrap up our discussion, we've journeyed through the realm of non-parametric tests, understanding when and why they're preferred over their parametric counterparts. We've delved into various types like the Mann-Whitney U, Wilcoxon signed rank, and Kruskal-Wallis tests. We've also weighed the benefits and limitations of these tests and seen them in action in real-world scenarios. Remember, understanding these concepts is not just about passing your exams, but about being a better pharmaceutical researcher. Keep exploring.